is, or for that matter, what you know as construction is mostly that what you see, right? So brick, cement, concrete, and all, right? But traditionally, it wasn't so, isn't it? So she will be putting the highlights of her research and her work. So I would request our student to please introduce her.
Good evening, everyone. It is my pleasure to introduce our speaker for today's Sitara seminar, Dr. Swati Manohar. Dr. Swati Manohar has been an assistant professor in our Department of Civil Engineering and at Indian Institute of Technology, Bombay since 2022. Her research focuses on heritage conservation, durability of construction material, and microstructural characterization for in situ applications. She was recently awarded Early Research Achiever Award 2024 from IIT Bombay, Associateship of Indian Academy of Sciences and Indian National Science Academy History of Science. Recently, she has also been conferred the Indian National Academy of Engineering Young Engineer Award. We are delighted to have her with us today. Welcome, Dr. Swati. Over to you.
I'm sorry, I did not on the mic. Okay. This is fine? All right. So those who could not hear me, I was saying that heritage conservation is an interdisciplinary area where architects, the traditional artisans, sthapatis, engineers, everybody works, but mostly conservation is predominantly governed by architects and not engineers. So here in this talk, we are going to see the engineering vision or engineering perspective of how to deal with heritage structures through some of the case studies here. And this is the roadmap of what we are going to listen today. I'll start by giving a brief introduction to the heritage conservation state in India currently, looking at material properties, different materials used, and their role in governing the damage mechanism. I'll get into a few case studies, specifically 3 case studies with stones and lime binders, which are the common heritage construction materials. And then we'll end with conservation approaches rooting from material characterization. So this is Sarnath. Very recently, last week, Sarnath was announced as 45th UNESCO World Heritage Site. And this is a brick stupa, as you could see. So here I'm introducing you to one material, which is brick. Similarly, you will have other structures which are mostly of stones and binders as lime. So India probably has the most richest built heritage stock in the world, and we are all proud of it. But at times when we go to these structures, we also worry about the degradation that you see. You don't need a lens to see that as well. So that makes you worried, which is true also. Most of these structures are in the verge of damage. Some are being damaged and being repaired, right way or wrong way. It's being done now. And most of them are made of stones, bricks, and binder as lime. In Western countries, they have a policy of minimal intervention with heritage structures. So if you touch a heritage structure for repair for another 50 years, you don't come back and do anything on that. That's a minimal intervention principle. But in India, we have not yet reached there. Basically because we do not know our heritage structures well. The materials are not documented, construction practices are not documented. So when we find a problem with one structure, we start from scratch. We start from no drawings are available. So we start to understand that structure from scratch. This is the state in which we are in, which is progressing, which is changing now. Because of this, we also are often doing wrong kind of repairs in these structures, which are having catastrophic effects. You see, you do a repair in 2 years, you will see that that's coming up. Many of us will be able to remember one brick masonry structure in our neighborhood, which is heritage, which is being plastered with cement plaster now, modifying it into a modern neat structure. But then when you're adding cement plaster on the structure, what happens is you're adding the dead load on the structure. You are sealing a breathable structure, thereby you are inducing stress built up inside. So that will come out in 2-3 years, and this has been seen in past 10-15 years. Now ASI, so Archaeological Survey of India is the body that governs conservation in India. ASI is controlling almost 3,800 structures in India. Now they have banned use of cement in these structures because of this. It's not clearly cement. They have banned use of cement in structures which are actually made of lime because of compatibility issues. So if you look at this structure in the right, so that is big temple in Tanjavur, which is standing sturdy, which is built in 1010 AD. But if you look at modern structures, you see that it starts getting damaged less than 10 years, even though they are designed for 50 or 100 years. And definitely strength is not the reason. Modern materials are high strength. We know to design better materials. The problem is durability and the exposure conditions. By durability, this talk is going to be focused more on durability, which is actually pore structure in the material. If a material is more porous or less porous, what does that mean in specific environment? So through this lecture, you'll also see that durability problems varies with exposure conditions. And when we know some structures are standing very good in some conditions after 1,000 years and 2,000 years and some are not, can we ensure durability of materials in structures when we build new structures? Can we learn something while to design materials scientifically so that it has much longevity? These are the questions that we are trying to address. Now I'm coming back to the story which I'm telling a while before. This doesn't work here. Okay, no. So here the first picture, this is just representative of a masonry structure. You are seeing stone inside, which is plastered by lime. When you're repairing it, if you are using cement for plastering, initially, inherently, it was a breathable structure. So vapor was continuously moving in and out, water might move in and out, and that is okay for these structures which are more porous. When you are sealing it with a cement plaster now to make it repaired or to make it new, you are sealing all this water, vapor movement, salt, everything inside. So pressure starts building up. Crystals will grow, it will exert stress. What happens when stress builds up inside? It bursts one day. In structures, it doesn't burst like us, but in structures, when pressure built up, cracks forms in those portions and cracks extends and then failure happens. And that new layer that you added will come out along with some of the heritage material, which is stone. This is why cement is asked not to be used in heritage structures anymore. But we don't know to make lime mortar as so also like in the past. So our research group, as well as many research groups across the world, are now working with lime as well. We are in the process of standardizing lime to be used in these heritage structures. Now, having the background set, you know some of the materials. Stones you just saw, bricks you saw in Sarnath, and lime is the binder. Now I'll get into 3 different case studies. One, I'm starting with the most beautiful material, which is Makrana marble. All of us are familiar with these structures, Taj Mahal, and this is Golden Temple. Even though these are marble structures, these are actually brick structures. They are brick masonry structure, just cladded with marble, cladded with thin marble and of course gold as well. And these structures are beautiful definitely, but we started with identifying the damages and causes of these structures. From Taj Mahal, this is Jaswant Hada in Rajasthan, and this is Dilwara Jain Temple in Mount Abu. So you're looking at different damages. See, we saw fragmentation, powdering, abrasion, cracks, biological colonization, encrustation, which is gypsum deposit, sugaring, which is powdering of the marble, and staining. So these are all manifestations. You see manifestations in different ways. What you need to do is finding the root cause of this. Among all of these, the most prominent I wouldn't say damage, but most prominent degradation mechanism that you would observe if you go to any of these structures, let us say, take Taj Mahal as an example, would be staining. So staining is very commonly seen, and in fact in Taj Mahal, they do methods for removing the stain, destaining methods periodically in every 2 to 3 years. What they do is something called poulticing. which is very similar to the facial pack we do. So you take a paste, they apply the paste over the marble. Upon drying with capillary suction, it will suck up the stains and all the dirt or dust from the marble, and that will be on the paste. On drying, you remove the mask or remove the poultice. It's called poultice. And now the material is cleaned. This is theory, and it's by capillary suction. Practically, this would happen only if the paste pore structure is much smaller than the inside substrate pore structure. Otherwise, that capillary suction wouldn't happen. So this was happening. This was being done in Taj Mahal for many years. And if you go there, you will see that the exterior is very white, especially after this process. But the interior is still yellow. So it works in the outside, but it doesn't work in the inside. And if you look at the reason, this is the hypothesis from our lab. So marble is susceptible to something called bowing. Bowing is just bending. So marble, because it's made of calcium carbonate, it is an anisotropic material. It expands in one direction when heated. So these are very thin claddings which are exposed. And while heated, it will bend towards inside like this. So while bending, the external surface will develop more cracks or fissures. And the interior cracks would get closed. So the pores are much smaller here. The pores are much larger outside. Now, if you're applying that facial pack or fuller in earth or poulticing, what would happen? The outside, it's very easy to clean. Stains can easily come out because the pores are larger. In the inside, it is much lesser pores. It's very difficult to get it cleaned. That is why when you go there, you don't see the inside clean. They are using the same poultice. So the solution is you redesign particle size and packing of the poultice material. So don't use the same poultice material inside and outside. This motivated us to work on this further and understand various other kind of damage mechanism. So this is just an illustration of what happens. Now, because of this increase in porosity, you have more pores. Acid, salt, humidity, everything starts more action on this material, and you will start seeing all those many kind of damages that you saw before. This is an example from Ranakpur temple. Ranakpur is a beautiful, huge marble temple, but then it is not as good as grade 1 Makrana marble. It has a lot of iron content in it. That's why it's looking black. So this is a photo I took from ceiling of the temple. You have beautiful artwork in the ceiling, but it is powdering and falling off slightly. And when we looked at it, we saw that from the rooftop, there were cracks which supplied water continuously to these marble claddings. And when water comes into this iron containing in marbles, you see that black lines in between. Those are iron minerals. So iron will come out and get oxidized. That's what you see as brown deposits here. And now you are losing the bond in your marble and it starts powdering. So the best solution was addressing the water coming from the top. And then this is a low grade marble as well. So coming to remodeling poulticing by adjusting the pore size of the material. So we cannot do trial patches in Taj Mahal or say any of these structures. We cannot also take marble from these structures and do it in lab. So what we do in lab is we collect good marbles, many marbles. We induce stains purposefully, turmeric, ink, iron, everything. And then we apply packs on this and then we see which one becomes more efficient. We also developed a MATLAB code which takes photo before and after the application and it will show percentage efficiency. So we did a lot of trial and error and we developed a poultice method by which we can alter the pore size and develop the right material for doing the poulticing and cleaning the marble. So here you are seeing soap nut washing. Soap nut is a natural bury. So you cannot use chemicals in marble because marble is highly susceptible to acidic environment. It will get powdered. So you bring the stains to the surface and then you do soap nut washing to clean it from the surface. Now, one of my PhD students is currently working on improving this further. What he is doing is he is applying an electric current also to this along with this facial pack or poulticing. He is applying an electric current that will take the anions and cations from the salt to two directions. So poulticing becomes much easier. That is what you are seeing here. So this is your sample, stone sample. You are applying current on both sides, which is packed with poultice, and you will see that salt move quickly to both sides. So this is underway. We have not yet found full efficiency, but we are still working on this. First case study was that marble and how it is being stained and how do we do destaining. Before starting second and third case studies, I want you to introduce you to something called physical salt attack or salt crystallization, because salt weathering is the most damaging mechanism for all the heritage structures, mostly, especially in India, because we have a huge coastal stretch. And salt crystallization you see in all these forms across our structures. It's not only in brick, in stones as well, but I showed the photos because they're the most prominent and easy ones to identify. The phenomenon is salt and water from the atmosphere gets into your material. On evaporation, water will come out, salt will come and precipitate on the surface, which is called efflorescence. You might see white patches on your surfaces. But this is okay. This might make your structure look ugly, but this is not damaging. If this precipitation happened inside your material, if the evaporation rate was higher, that is going to damage your material. That again will build up stresses. The salt will not have space to grow inside. Material will crack. That is salt crystallization. And because of that, it is known as one of the most damaging material, not only for heritage structures, any structures which are exposed in these conditions. So this is an example of stone as well as brick structures heavily affected by salt weathering. The first picture is Mahabalipuram Shore Temple. The bottom one is Trankbar brick fort. Now, the mechanism of salt crystallization is, if you're having pores in a system, this is a scanning electron microscopic image of one of the samples. If you have pores in the system, salt water will get in. Subsequent dry wet cycling, the concentration will increase, salt will precipitate. If it grows, if it has space to grow, it's absolutely fine. But if it doesn't have space to grow, it will exert pressure and crack the material, and the material will fail eventually. Now I'm starting with the second case study, which is from Rameshwaram Ramanatha Swami Temple. This is made of, the temple is also lying exactly on the seashore. It is made of coral limestone, or it is called floating limestone because the density is very, very low. Some variants will have density less than 1, but the ones I tested had density more than 1. This is the microstructural view of the sample, and one part of the structure was damaging. So the authorities wanted to know whether it's because of salt weathering. When we looked through a scanning electron microscopy, we saw that this is the structure of it, and these are quartz crystals which are surrounded by a flowery lining like this, which is very, very porous, which was magnesian calcite, Mg plus calcite. And this is very light, very porous and fluffy. And because of this, actually the stone is very porous or floating. That's why it's called floating stone. Now we wanted to know whether this material will get damaged with salt or not. So we washed the material, dried it, and then we subjected the material to very rough salt weathering cycles. And we saw that after 1 month of cycle, no damage at all. Not even a slight damage was obtained or was observed in this sample. When we looked at the reason, we saw that there is something called preferential deposition. These are salt crystals. Salt crystals are going and depositing in this flowery shaped magnesian calcite region only, and not the small crystals. So if a salt is precipitating in larger pore where there is space, it will not damage the material. So we said that, okay, this material will not get affected by salt weathering at this place. This is having good resistance. So then they looked out for other reasons. So then we figured out that it was wind plus seepage, etc. Coming to the third case and the last case. So we looked at marble. We also looked at coral limestone, 2 different stones, and this is mortar. Traditionally, we were using lime mortar in all these constructions. In India, we have the practice of using a lot of organics, different fruits, different dals, anything that is a source of carbonates. This is because lime generally hardens by absorbing CO2 from the atmosphere and then hardens into calcium carbonate, which is a really slow and excellent process though. But now we don't have time to wait for 1 year for your structure to get strengthened, so we don't use lime anymore in newer structures. So anything that gives extra CO2 to the material would ideally enhance the process. That's why people were using urad dal, different kinds of dal and fruits, ferment it. So one is jaggery. And here we wanted to explore, can we standardize using jaggery, which is sucrose, cane sugar, in some way to say that this is the dosage, this is how you should use it so that you get an excellent lime-based binder. This was a study. We also wanted to know what is actually jaggery doing to this material. People who works at sites, when we go and talk with artisans, they say that jaggery is a magic material. You add in lime, it gives excellent fresh and hardened properties. So what actually we did was, lime is really slow in curing and strength gaining. So we added pozzolans, which are silicates, aluminates. We added slag there. That will enhance the reaction rate. So you get it quicker than traditional lime, but not compromising any of the other properties of lime that we achieved with jaggery. When you add jaggery, what happens is, in lime, you are having calcium hydroxide molecules. So when CO2 comes in, it will react with calcium hydroxide and you get hardened calcium carbonate. So traditionally, if you're applying on a wall or a structure, the initial external surface will get carbonated first, and the interior will really take long time to carbonate. If you're having jaggery, the jaggery molecules will go and adhere and get attached on a calcium hydroxide molecule like this. So the external surface is not immediately carbonated. When CO2 comes in, it has space to go into the surface and it starts carbonating from interior to outside. So you're getting a better carbonation, quicker carbonation, and proper carbonation when you're using jaggery in lime system. And then we optimize the dosages. So this is a thin section microscopic image from a freshly mixed lime. And you can see that jaggery getting attached over calcium hydroxide molecules. And then we evaluated it at much depth using Raman and other spectroscopic measures also. At larger scale, what we did was, we made cubes with jaggery and without jaggery lime, and we subjected them to accelerated salt weathering cycles, extreme salt exposure and drying. And here we are measuring the weight loss after every cycle. The black one is the failed sample after 20 cycles, which did not have jaggery, but it was enhanced with pozzolan. But on the top two ones, when we are adding jaggery, it was not failing at all. So it had good salt weathering resistance like the coral limestone. When you're looking at the reason, it was because, so jaggery samples had efflorescence, but efflorescence is not damaging. The other sample did not have efflorescence, but salt crystallization happened inside the material and the material just bursted. You are seeing a small part. So it just broke into 2-3 pieces. So when you're having jaggery in your system, it acts like a salt transport system. You're having larger pores in your system, and the salt or water can move slowly to the surface and have efflorescence. Whereas the other one, the pore structure is very catastrophic. Crystallization happens inside the material and the damage happens. So here I have tried to summarize it in some way. This is a jaggery added system. And this is the work from one of my another PhD student. In a jaggery added system, you are having larger pores which are very uniformly distributed because of those calcium hydroxide attached with jaggery molecules. And there, during evaporation, the movement of salt and water is very normal. It comes till the top and you are having an evaporation front here. If this is the lime mortar cube we are testing. So your evaporation front is close to surface. You have efflorescence. It is not damaging the material. But in other case, you are having small pores. So salt crystal precipitate inside. It doesn't have space to grow or move. It causes cracks in the system. This is your evaporation front and it gets separated into 2 pieces. So you are actually modifying the pore structure of a material to get a better performance. Those are the 3 case studies, 2 on different stones. Same will happen with bricks also, and 1 on lime mortar. So in mortar, you can design material pore structure. In stones, your responsibility is to choose the right stones, which are having the right pore structure. So that's all the lecture about. If I want you to remember 3 points from this lecture, that would be, most durability issues are governed by pore size distribution in materials. It's not chemistry of the material. It's not because marble is more reactive. It's because of pore structure of the material. You choose pore structure according to the exposure condition. Second point is, when you're repairing a heritage structure, the most important parameter is breathability or compatibility of materials for breathability. If a structure is inherently breathable, you cannot block the breathability. You should choose a repair material which is very similar to the existing material. And the last point is, depending upon the exposure condition, you engineer your material or choose your material. So all the two case studies you saw here were from salt weathering or marine condition. First case study for marble is from a dry condition. That's why you see a difference in the mechanism also. Thank you very much for their attention. Are there any questions?
Yeah, so any questions, anybody?
Hello, ma'am. I just had one question. All the practices that we're introducing in the conservation system, are they also applicable if we try in the regular construction mechanisms? All the methods that we're using, because they're considered very exploitative.
We use many of these in regular also. For example, marble we use in modern structures also. Ayodhya Ram Mandir is a modern structure, but it is designed for 1,000 years. So the measures, it is made with materials which will stand for 1,000 years. So when you are designing a material structure for 1,000 years, the first point is you don't use steel in the structure. Ayodhya Ram Mandir doesn't have any steel because it will corrode. So when you're choosing material, all of these are material specific. It is not only for heritage or modern. If you're using stone, this is what you should follow. If you are using lime, this is how you should be using lime. And if you are repairing a heritage structure, the point is you should study what those materials and do the repair accordingly. Do a compatible repair. So many of them are same with modern materials, modern structures if the material is same. But if the material is cement, the practices are different.
Okay, and can this be adopted in regular, the normal construction practices that are normative in the country?
Stone we are not using. Cement concrete is much popular because of its cost and easiness to work. You do it today, tomorrow your material is completely cured. And the cost of 1 kg of concrete is less than 8 rupees. Nothing can match that. Stone, if you have money, if you have time to wait, if you have skilled labors, you can do stone construction today also. Lime also is time consuming. That's why we are not using lime instead of cement in all these construction. But there are many firms which applies only lime, uses lime when they are the lime gives more thermal comfort in the material because it's more porous. So it is, but you might not be able to do for faster construction at all. So there is always a trade-off between what you want and then you go for it. Understanding the materials is the key to make the right choices.
Thank you, ma'am.
Hello, ma'am. Myself Mihir. I'm a first year student for MTech. By background, I'm an architect. So I have a few points that I noted, and I want your opinion how scientific approach can actually help us to deal with those things. First is like, as you said, there is no documentation of the processes that were there, like earlier what materials they were using. Obviously, we are getting the materials, but they are weathered after
Correct.
many years, and maybe the composition is not exactly same as it was earlier. Right. Then the craftsmanship, as we say, then masonry structure, the same masons are not present, and we might have some issues while actually even if we like create similar material, then also having the same masons, same artisans to actually build that back are not available, because that is more of generational knowledge which might have not been documented in written format or any other format. And then one point you said was breathability and compatibility. So I have one thing there. There are many temples across the India, majorly in South India, the Nagara, Vesara style. They are in either black like basalt stone or sandstone. So whenever there will be some like weathering happening, when something is, let's say, broken, and we want to fix it, how the new material is going to be attached to it, what kind of materials we can use to bond those the gap between the old and new material. These are my questions.
Okay, thank you. I'll start by answering the last question. The others I will forget and I'll ask you again. So in South, mostly you see granite because that's the most available stone in South, in Kerala and Tamil Nadu. If you come to Maharashtra, it's all basalt here. There's a black basalt and black granite there, and sandstone in the central and northern India. When you're replacing it, the policy is you replace it with the same material. But there also in these structures, the binder is mostly lime because cement was not invented that time. So if when you are replacing it, you don't mix lime with cement, then in that case, you are creating a layer in between which doesn't connect anymore. So high chances are that they'll get separated because of this deposition. You're blocking breathability, water vapor or anything inside will come and will get deposited just below the new layer. So that can come out easily. That's the reason we say that go with compatible materials so that whatever the natural moisture transmission process, you don't affect, you don't block it. That's the only reason, but you use similar material. Basalt, if then it is basalt, again with similar pore structure. If it is sandstone, it's the same. To bring an example for this, in temples like Jagannath Puri, Sun Temple, Konark, you will see panels with very intricated artwork there. But when ASI is replacing that, they only try to replace with similar sandstone, but don't try to replace the art in same way. So you will see in between very plain panels. And you will feel hurt also to see that, oh, we have damaged this and now it's plain panels. But then if we don't have the skill to replace, as you said, that. But if we try that, are we manipulating this is heritage and that is heritage? To avoid this confusion, this is current ASI stand, which is controversial also, which has both. So there, everywhere we are trying to use same material, but don't try to copy the art that is being transferred. Okay, what was the other question?
One was like, other than that, I think is that one is like cost of repair, like how the cost of repair, like how it differs from the materials, basically how expensive it is to use those materials again.
Heritage conservation is expensive than modern construction, but we always do something called heritage impact assessment. So heritage structures have a cultural value also. Even if you want to do some modernization, when development happens, a metro is coming up, a heritage structure is standing nearby, you want to take a decision whether to take the structure off or will this damage the structure by vibration also. Every such case, even while doing a repair, people want to know, is it worth to put this much money to do this repair? So we do a heritage impact assessment. There is a proper protocol for that. And then you evaluate everything, the tourism value, cultural value, development, and then you finally take a decision based on that report. So it's not like you have to do the repair putting this much cost. It is a judicial calculation. Thank you.
Anybody not from architecture background? Because I think architecture should dominate this discussion.
Hello, my name is Gaurav and I'm a PhD student at Sitara. So my question is on, no, I'm not. My question is on same line, like you mentioned about the Sarnath Stupa in the beginning. So I just Googled it and I found like it's something 249 BCE.
Yeah.
So somewhat 2,400 years today. So have you come across some maintenance practices which were there in history? Because what I can see is like the ancient practices, skill and labor, we are trying to repair with the contemporary civil engineering knowledge. Let's say whatever which has been developed in last 30-40 years. So there must have been, because the structure are still in somewhat position, standing there for 2,000 years, there must have been some techniques, some skills to maintain them. So what are those skills and why do we want to replace them with the modern practices of last 30-40 years? And are they, equivalent to those, better than them? Some insights on this.
Yeah. So we are not advocating to replace those with modern practices. Only when some things are not working. For example, ASI was also using cement only for repair before 10-12 years. When they saw that cement repairs are coming off in 2-3 years and many studies happened in this area and show that this is not right, then ASI banned the use of cement. Now they are starting using lime. They want to understand how lime works. IS code is being developed on how to exactly standardize the lime so that any engineer can also do that, because we don't have skilled labor, as they say. We need that standardization process, so we are in that process. Coming to ancient maintenance practices, so these structures, Sarnath, for example, they are not in heavily exposed environment as well. So brick structures mostly otherwise they're used in residential or low service life structures in other conditions, and monuments were made with stones other than these stupas. We also have a stupa very close by, which is more than 1,000 years ago old, Nalasobara stupa. So these stupas we have seen that the bricks are itself is of very different quality. So if you look at the brick, if you do an X-ray diffraction analysis, you can find out the raw materials used and the firing temperature. And when we looked at heritage structures bricks, we saw that they were fired at very high temperature during that age. We cannot decipher how did they do that, because it's quite difficult to attain very high temperature firing that time. And when you do something at very high temperature firing, if the clay material is non-calcium also, you will get round pores in the system, normal uniform distributed round pores in the system. That will enhance durability of these bricks. This is a finding from my PhD. In fact, I worked on bricks during my PhD. Other than that, there was no practices other than cleaning it properly. So for at least in bricks stupas, there were no practices. So when people were using mud mortars, one challenge was biogrowth in between this. So when biogrowth happens, trees grow inside and cause cracks, water further inside. So regular cleaning is something they are still doing in these historical sites. And wherever they are not doing it, you will see the damage also. So another example for this is in Hampi. In Hampi, you will see that top portion of all the temples are actually brick now also. And in some of the structures, there are 2000 plus structures. Some structures, they don't do a cleaning regularly, and you see biodegradation, and you will see that that's coming off. So other than cleaning, I don't think there was any specific maintenance practices going on these structures. Maybe I'm unaware of them also. Maybe locally there would be certain things at some places.
Very good evening. Very good evening, and thanks for the wonderful talk. Ma'am, my question is little bit than this topic. See, we have a lot of structures, ancient structures we are having, and whatever the civil engineering or architecture we are learning right now, it's Hooke's law or whatever maybe, it's been taken from the Western or the other countries. So for such indigenous construction, do we have any institution or do we have some entity which promoting or making awareness about all these structures? How the olden structures were built, what was the technology? Because in foreign countries, we have Vitruvius and all those people, those who have documented all such things. So in India, is there any institute which promotes such things?
I do not know as institute. DST has a wing called Science Heritage Research India, which looks at heritage research and give funds for that. IKA started giving funds for doing research, but not on heritage structures. It's on a wider domain. And there are, I did my PhD at IIT Madras. There is a center called National Center for Safety of Heritage Structures. That's a small center funded by Government of India, MHRD, but looks at heritage structures specifically. So we have people working, but I think it really has to grow more. So we don't have very established system like in Western countries. As you see, in Western itself, Europe, if you go to US, you wouldn't find many. But in Europe, you will see very well established system for mostly all the construction practices. Here we don't have that.
Okay, any other non-architect or the if you have finished, then architect.
Hello. My question is that if we add edible materials like pulses and jaggery in construction buildings, is there not any threat of pest attack?
No, jaggery is actually sucrose. Jaggery is cane sugar, which is more than 90% sucrose only. Sugar is already a retardant that we use in concrete also. So you add sugar, your concrete will not set. If you want to set your concrete really slow, for example, you are taking your concrete mixer to a far place and you don't want it to set very quickly, sugar is a retarder. There are many other chemical retarders, but sugar is a retarder. So this has been used in construction quite long. What happens in this case, for example, jaggery with lime is, it will form a chelation. It will form a complex and attach around calcium hydroxide. And that will again change to fructose, so that it will be a complex. And eventually it will be broken up further and will remain into protein forms and get deposited in the forms, in the pores. So it will not remain as an organic there anymore to get degraded or have pest attack.
Hi ma'am, myself Gaurav, first year PhD at Sitara. So we talked about the materials that reminded me of the housing practices in the mountain regions. So the traditional housing practices and the residences, those used to be made of stones, woods, and urad dal, as you mentioned. And the maintenance used to be done with red soil and cow dung as well, which we saw during our Govardhan Eco Village tour as well. There they were using the cow dung and red soil. So my question is that, and during my fieldwork in Uttarakhand, I heard that people were saying the ancient or the older structures used to be more reliable, and they used to withhold more in that region and more compatible to that region. And the modern structures, they are not that compatible. So is it possible to use the ancient practices in this modern time, in specifically in the mountain regions? And what are those factors, like as I heard during field working, those used to be more sustainable and last long. What could be the
Thank you for that question. This what you're talking about is vernacular constructions or context-based construction systems. For example, in mountain areas, earthquake is highly common. So these structures, there are specific structural styles called Daji Diwari system, Tak system. So for example, in Shimla, if you go, even the governor is staying in a Daji Diwari construction system. In Daji Diwari system, you have stone masonry, but braced with wooden braces. So the whole wall is divided into so many panels. When an earthquake happens, all these panels will shake, there will be cracks, but the structure will not collapse at all. The structure are surviving so many earthquakes, they don't collapse. But when you are having modern construction, which are not designed for seismicity, it's very rigid, it cannot handle a shaking and it will crumble. So in modern structures, how do we do seismic analysis? Seismic design is you create a base isolation. So the whole structure is not rigidly fixed to the base. So even when the base is shaking, the structure will shake, but it will not collapse because it's not rigidly fixed. So these system, in Assam, there is something called Ikra housing, which is, Ikra is kind of a plant like bamboo. So you make a house with a wall with panels of bamboo and then fill it with masonry. So that's how they are resisting resisting earthquake. Similarly, in highly heat, for example, in Gujarat and Rajasthan, there are something called Santal hut, which is for heat resistance. You feel much thermally comfortable inside because the walls are much thicker, made of mud-based walls on both the sides. So when the wall is thicker and thermally comfortable material, you don't feel the heat inside. So India, not only in India, in every country they have, so in US, Arizona is the most driest place, most heat place. There people use mud construction often. So every place would have its traditional locally context-based architecture. That's what you're saying about. And people still locally use it because it's made from local materials, made by the local people for their own use, and it is best for that particular environment. But then scaling it up is difficult because the practices are not standardized. You cannot say an excellent building material would be just make a mold, put stones and put some cement in it, you will get building blocks. But can you standardize it? Will you be able to find exactly similar stones every time? The strength is going to be differing. So that's why it is not standardized or scaled up. But still, me and Charu used to run a course called Vernacular Construction System last year. We will again float it. So there we teach this specifically. So there are people who are following it. Ministry, government is also doing these kind of construction for mass house projects in different parts of India because it's easier there and it will work well there. But it's a little difficult to scale it up because the same construction will not work everywhere, every place in India.
Hello, ma'am. I am Hemant, a PhD student. I have a question. In one slide, you mentioned about the longevity of the civil structures. So if you compare the current structures and old structure, there is a quite gap or maybe a difference in the longevity. As mentioned, there are two factors which are impacting or having impact on the longevity. First is the raw material which is being used, and another is the environmental factors. So in current scenario, if we enlist the environmental factors which are affecting the civil quality, so as per your opinion, which is the topmost factor which is affecting the quality or longevity?
I didn't know among environmental factors.
No, which environmental factor in current scenario is
Okay.
affecting the longevity of the civil structures?
So in modern structures, so in modern structures, the most money we are spending is for corrosion. So all these structures we are designing for residential houses, we design for 50 years, bridges we design for 100 years, but they are all getting degraded in 10 years or less than that because steel is getting corroded in concrete. And steel is corroding either because of chloride attack, which is from salt, marine exposure, or because of high carbonation, high carbon dioxide in the environment. So if you see steel rusting in Delhi, that might be because of carbonation. In Mumbai, it might be because of chloride attack. So corrosion because of salt exposure or carbonation is the most damaging issue with modern structures. And we are spending such high part of our GDP in repairing of modern structures just because of corrosion. To your question, I wanted to add something about jaggery. So the jaggery addition is very low. It is only less than 1% of the whole binder. But traditionally, if you go to site, I saw myself that people just add kilos of jaggery into it because people just know that jaggery is added. Nobody knows how much to be added. So in such cases, if you're adding too much of jaggery, that might not get properly dissolved in the system, and that can maybe attack pest also. Because once I have seen that ant coming, maybe it was too early in the stage also, but this is a practice that made us think that we should actually clarify how much is to be added and when, how to be added. Need not ferment also. We can ferment in water and then add, but we found that non-fermented jaggery is actually better than fermented jaggery.
Add in that point as vernacular construction system as we talked about. So can we say that it is declining because of the new modern structures, we somehow connect it with the social status, with the modernity or the modern adaptation of modern practices, and somehow this is increasing the vulnerability in because these structures are not compatible in those areas and we cannot standardize as you said. So can we say that it is increasing the vulnerability in those areas?
We can, when we are constructing something in those areas, we need to be extra careful about designing it specifically for this. But if you are adopting their own local technologies, if you can ensure quality of that construction, that is the best. It is declining, I would agree, also because we don't have it in curriculum. No civil engineers learn any vernacular construction system before they graduate out. They are only exposed to, including me, we are only exposed to cement, steel and concrete when you are graduating. So, and we are only going out and doing all the construction. So how do you expect that we will construct something else? So now there is a change, there is a small shift happening where curriculum we are also introducing to all these different materials. There is awareness picking up. So we hope it will change. One problem with vernacular construction we face when we go and see people how do they construct is that also get diluted because it's ancestral transfer of knowledge. There is no systematic practice. There is a construction called Kathkuni construction, which is also earthquake resistance. So in Kathkuni, you have stone blocks, stone walls, and in between you have a wooden layer. So currently how people do, it used to be an excellent construction. Currently people use good stones but very bad wooden layers in between. So that wood will degrade quite quicker and it is losing the whole charm of the structure. So that the quality is also diluting. So they are generally called non-engineered structures. So if we study that more and teach this is how this structure is to be made, maybe we will see a difference.
Yes. Anybody else from the other side? Oh.
Okay, I will give it to you. Thank you, Professor, and congratulations for your award. And my question is how, like, from the cracks, we can see it from outside. But for the assessment of inner health of that old structure, what matters is the sound is being used or what are the sensors?
Yeah, we have several tests called non-destructive testing in civil engineering. Mostly they are common in modern structures. So we know that you do the testing. If this is the value, it tells that the structure is good or bad. So we cannot use those charts in heritage structures, but we need to calibrate it ourselves. So we use some of the tests. For example, there is a camera called infrared camera. Many of you might be knowing. You go look through the camera, you can see temperature differences throughout the facade. So you will see where all cracks would be there, where all moisture traps would be there. So then you go closer and have a closer look. This we have done in Golden Temple. So we identified and then we removed the golden plate and then we saw inside the brick masonry, we could see where moisture traps were there. And this helped us to map the moisture source as well. So this is just one example, IR camera. There are several such. There is something called borehole endoscopy. Just like the endoscope, we put it in our mouth. We drill a hole in the heritage structure, small hole, insert the camera with the tube. That will capture the thickness of the wall. If there is some other material used in between, cracks are there. So similarly, but that is minor, small. It's a little intrusive. You need a hole, but you can fill the hole. It doesn't damage the structure. Like that, there are several tests which we generally do in heritage structures, but getting permission from the authority to do these tests is the biggest, toughest part in this profession.
Namaste, I have a query. Previously, there was a question about recorded texts on ancestral, traditional heritage structures and so on. Are there vernacular texts in local languages? For example, in Malayalam, there is Tantra Samuchayam and so on in Kerala Vastu practices. Is it common everywhere? And if you have come across any text, whether it is in Sanskrit or vernacular languages, is there a specific challenge that you face in this context? For example, interpretation. I'm from design background. I work with paintings, for example, Ajanta paintings and so on. So one of my challenges is the text prescribing what is to be done, or is it describing a practice that existed and so on and so forth? So
yeah. So we have ancient text in some cases, not everywhere. But then interpreting it is actually difficult. We normally take help of people who have expertise in language or so. So we work with Jain Temple Trust in developing a binder called Vajralep, which is a traditional binder followed in their text by mixing 14 different organic compounds collected from different parts of India. Some are having resin, some are very longeable. So they are trying to replicate themselves, but they are not able to. So they want us to do it in our lab and see how if we can standardize that, so that they use only that binder for as an adhesive for their marble statues. So when looking at the text and translating, one problem we found that they would say, okay, mix 6 ingredients, this much each, and we don't know what that is. Now, something similar to that, but we really don't know how much it was. It's not in grams or anything that we know in volume. So then you make your guess, you talk with many people who might know that and try to figure that out. But still we are not sure whether it is exactly replicating that or not. That's why they were also not able to replicate it when they were trying. But in lab, you do a lot of trial and error, you do testing, you have records on how this mix was performing and a slightly different mix performing, and then you converge to one point. So this is always a difficulty.
Hello, ma'am. I am Shruti and I'm a second year student at Sitara in Tech. I have 2 questions. One is about the marble that we were talking. It gets stains, and then the tests were done in the lab. But my question is, there are a lot of external stimuli affecting that structure in that area, be it wind load, humidity. How is the layer being accurate or functioning in that situation, since in the lab we have controlled environment? And second question is about the jaggery. Since jaggery is hygroscopic, so does it affect the early strength of that structure, or are there any residual areas where the uneven setting is happening anywhere?
Okay, I'll answer first question. Okay. It is very true that you cannot replicate in lab the actual situation because there are complicated factors, multiple factors acting on it. But in lab, what we are trying to do in this case is enhancing that capillary suction, by which anything can be sucked or absorbed by applying a poulticing layer. So that deposits can be, for example, in Agra, it's mostly sulfide deposits. That deposits can be any stain, but the stain removal by capillary suction is what we are attempting. So that's a cleaning process only. So, but in any case, for example, if you're looking something specifically for salt, that could be an issue. So this is a generic issue, but always lab results cannot accurately replicate what is happening naturally. Even all the accelerated weathering we do, Even though we do in lab, we know that it is not exactly replicating what is happening naturally. But then we cannot wait for 1,000 years to study something. So in lab, we have to do it in a month or so. So we have protocols which are also, so the committee who developed this protocol work for 5 years, 3 years, and then develop it, doing round robin test in different parts of the world, and then see that all the tests are giving the same data. That's why we generally form all these protocol for testing. Jaggery is a hygroscopic material, so it is actually doing good for the material. Lime, working with lime is a little difficult than cement. So jaggery was, people traditionally were adding jaggery because it helps in fresh property. You get really smooth and easy to work with lime. If you mix it, it will stay like that for hours. So you mix it one day, the whole day you can still work with it. But for cement, if you are finishing mixing, you need to immediately apply that. This is because when jaggery is added, this is even better, because jaggery is a very good water retainer. So it retains water in the material so that you have a very good workability over time. And if jaggery quantity is high, it can cause what you asked later. So the quantity is very important. It should be very less. So civil engineers would know this. You have something called super plasticizers that we add in concrete. You just add one drop of it. It's just 0.2% or something to the whole concrete. And then you see that your dry concrete will just become like a dosa batter. It can just flow. That's because that's also attaching over cement particles and releasing all the water which was already trapped in. The jaggery also does the same.
Doesn't affect the early strength of the concrete, right?
If you are only using lime and jaggery, the process is going to be slow because it is a water retainer. So in one slide, I had showed that we add slag or some silicates or aluminates also. So that is enhancing the curing process, and then your jaggery is acting as a water retainer. So you are balancing that out.
Okay, so how many more questions? I think you all have been quite inquisitive. That's really great. But can we have a quick count of how many more questions? Only you? You also? Anybody else? Okay, great. So last question.
After that, you can always write to me. Okay, I'm here only in IIT. My son is going to kill me if he start getting hungry.
Hello, ma'am. My name is Shrutika. I'm second year MTech student in Sitara. So actually, I had a question related to, so in conservation of heritage structure, it's always been controversial about if a old structure is losing its strength, you reinforce it or make it stable. Is it or is it more honorable to just let it fall and be remembered as a structure it was before, rather than using some unconventional method to just support the structure, but it does not actually does true justice to the material or the texture of fabric of the place? And second thing I wanted to ask is same jaggery. Because jaggery, every batch is different. So you cannot actually standardize a particular jaggery if 1 kg of jaggery, but whatever, you cannot standardize the actual process. So is it gonna be not easy to standardize this and make it as a commercial material?
Okay, thank you. Oh, I forgot the first question. What did you ask? Okay, I got it. So it is always controversial to decide if this is the measure to be done or not. But there are cases when something is falling, it will not retain. Do you think it will always tell a story to the future generation if there is no remains? So there are certain situations in which you have to take a call whether you need to retain something. For example, in Hampi in 2024, one whole pavilion, a few columns just collapsed as such. Now the whole authority is worried because there are 2,000 structures of same material in same exposure condition. Are we going to be silent about it? So they started doing an active conservation on all of those structures. So there are, you will see very wrong methods of conservation also. You will see that something is erected with a stone wall when it was a brick masonry or something plastered. So these are wrong practices, I would say, but there would be people who on the both sides as well. But again, the heritage impact assessment is the standard protocol that will help you to at least you have some justification saying that this is why you have done that. One example is Upper Aguada Fort in Goa. It is a highly crowded place, but it has only one small entry. The authorities want to do one more entry for exit so that they can manage crowd, but that might alter the structure. You don't know the stability of the structure. So it's a controversy there. So always, if you try to modify any structure, it's a controversy. But if it's something about falling the structure completely down, then I think better to take an effort. But then among all the efforts, you can go for the best compatible effort. Jaggery, when we started this, we did this because we went to the site, we saw that people were adding tons of jaggery into their mix, not knowing how to add and how much to add. But then asking them not to add jaggery is wrong, because I also do not know. I know that jaggery adding is good, but how, not how. So we started with jaggery. That's my first PhD student's work. But we standardized jaggery as this much percentage of sucrose in it. Now we are replicating all the studies with sucrose. Sucrose is more standardized form, where in European countries also people use sucrose as a retarder in cementitious materials. So this is the next step. Jaggery, getting the exact sucrose content is difficult, but throughout this research, we tried to keep the same source and same percentage of sucrose in it.
Hi ma'am, I'm Prathamesh. I'm a PhD student at Sitara. So my question is, since there is a discussion on the knowledge that help to build the heritage structures versus as against the modern engineering knowledge. So my question is, do we have with the modern engineering knowledge, do we have the capacity to claim that we can build a structure press that would maybe last for say 1,000 years as of now?
I think we have. We have. See, more, if you look at older structures, you start with pyramid. Most of the structures are overly designed, highly redundant, and relies on stability, geometry, and mass. That's how most of the structures were when you start with Roman architecture. They're all huge and very stable structures, only compression-based structures. So here you see this beam, this is under tension, but stone cannot take tension. So you don't see such beams in those structures. You will only see arches, which are all in compression. So they knew that engineering that we also know now. I think what we don't have now is the patience to work, time, and we have quicker alternatives now. But then we are seeing efforts where people are actually designing structures for 1,500 plus years. So my Vipassana Pagoda is designed by one of the company. He started a company, but he did PhD from IIT Bombay many years before I joined here also. He works only with traditional construction practices, traditional materials. There are people who design such structures. Ram Mandir is designed for 1,000 years. Now we are probably would be working on another structure which is also going to be designed for 1,000 years. So we can design structures, but then it is true that we don't have the skilled labors, but we have other alternatives. How do we leverage that is up to us. Thank you very much. You guys were very, very patient. I have not seen such an audience who are so interested in asking questions and being patient for so long. Thank you very much.
So great, I think, yeah, great. So all of you, I think you made Sitara proud in the sense that holding on for so long. One very inquisitive question to all of you, because we are talking of heritage constructions, is it good to have buildings to last so long? Question number one. And what kind of civilizational footprints are you going to leave behind? Okay, because traditionally only the fort, or for that the temple architectures, were made to last for thousands of years. Other than that, if you see, whatever the livelihoods or living zones, you don't find any footprint other than the brick-based Harappan constructions. Okay, and with the current modern practices and the technology capability that you have to have a Google map view of any location where habitation is there, okay, the kind of footprint that you are leaving behind and how long that is going to stay back and how you are going to deal with, and what you are giving forward to the people or the future generation. So just as a food for thought, just please think. All right. So all of you, thank you very much. And I think let's all come together to honor Professor Swati. We have this handloom scarf that is our traditional gift from Sitara to all the speakers. So, Professor Swati. All right, great. Thank you all. We can close the session now. Thank you.